welcome to learn algorithm design and analysis course. In this session, we focus on unit 3, and unit 3 in the first lecture we focus on what is a greedy method. We have already seen several algorithm design strategies. So in this session we focus on just revisiting the various algorithm design strategies that we have discussed earlier, and then we move on to the general form of the greedy method. Then we see how to apply the greedy method to find the minimum cost spanning tree for the given weighted connected graph. These are the objectives in this session. First, let's revisit algorithm design strategies. We have already listed in unit number 1 itself. There are different algorithm design strategies available to solve the real world problem. For example, we have seen divide and conquer, greedy method, dynamic programming, backtracking, branch and bound, These are the different algorithm design strategies that we have listed earlier. Divide and conquer, we have explored when the given problem size is large, we need to divide the problem input into smaller sub-problems. For example, having n inputs, we have divided the n inputs into k sub-problems n1, n2, n3, etc., nk. Then we have applied the divide and conquer logic to each of these sub-problems. So we have obtained the solution to the sub-problem with the input size n1, then solution to the sub-problem with the input size n2, etc., solution to the sub-problem with the input size nk. Finally, we have combined the solutions of all these k sub-problems, so that the solution to the problem P with n inputs is obtained by combining the solutions of these k sub-problems. This is the logic of divide and conquer. We have applied this divide and conquer logic to the searching problem as well as sorting problem. In searching, we have seen a binary search logic. In binary search, we have applied the divide and conquer logic. Then in a quicksort algorithm, please recall that we have applied the divide and conquer logic. Divide and conquer logic can be better implemented by using the recursive formulation. So recursively we can call the procedure until the termination condition is satisfied. So divide and conquer, this is one kind of algorithm design strategy that is applicable to solve a variety of problems. Particularly, we have discussed the searching as well as sorting algorithms. Second way to solve a problem using a good algorithm design strategy is a greedy method. Other than that, right, yet to see, right, what is dynamic programming, backtracking, and branch and bound. These three are other algorithm design strategies that we are going to discuss in the coming chapters. So in this chapter, we do like to focus on what is a greedy method. Greedy, right, as the term implies, this is one kind of algorithm design strategy. Algorithm design strategy. Like divide and conquer, greedy is one kind of algorithm design strategy that applies the heuristics logics. So greedy method, this is most suited to solve optimization problems. Optimization problems. So with respect to the objective function, right, either the minimization or maximization, we can apply the greedy method. So before going to see, right, how to apply the greedy method to solve optimization problem, first let's focus on what is the general form of a greedy method. Assuming that the problem requires n inputs. Suppose the inputs are stored in an array, capital E. First index is 1, last index is n. So clearly A1, A2, A3, etc., An, these are the inputs to the optimization problem. In case when the solution to the problem is taken as the subset of inputs, solution to the problem is taken as the subset of inputs, in order to satisfy some constraint based on the satisfaction of constraints of the problem, then we can better apply the greedy strategy to solve the given optimization problem. So please understand first, when greedy method is applicable, greedy method is applicable whenever we have an optimization problem in that the solution to the problem can be taken as the subset of inputs of the original problem, then greedy method is suitable. Greedy works, right, in terms of stages. That means since we are having n inputs, we need to consider one input at a time, one input at a time. We need to check if that input results in a feasible solution. If the input results in a feasible solution, then that input is added into the solution vector. So the feasible solution is a solution that satisfies the constraints of the problem. Feasible solution satisfies the constraints of the problem. So considering one input at a time, check if it results in a feasible solution. That means if it satisfies the constraints of the problem, then it is considered a feasible solution. Then check if a feasible solution optimizes the objective function. Optimizes the objective function. That means any feasible solution that optimizes the objective function is taken into the actual solution vector of the given problem. So in this logic, applying the greedy method, we need to consider the n inputs. Having n inputs a1, a2, a3, etc., an, we need to consider only one input at a time, check if it results in a feasible solution, then try to check if the solution is optimizing the given objective function, then include that solution or include that input into the solution vector. Finally, update the solution vector so that this solution is clearly a subset of input or subset of inputs. So whenever we have a solution, that solution is viewed as the subset of inputs of the given problem, that stage greedy method is applicable. Greedy method is applicable to find out the better solution or to find out the exact solution. Now first let's see the general form of a greedy method. First let's write algorithm. Since we have already written the general form of a divide and conquer, please recall that algorithm, divide and conquer, then we have given the input size. The same way, let's try to write the structure of a greedy method in the algorithmic style. That's all. Algorithm, greedy, the input parameters are A array, then n represents n inputs. So in this style, what is capital A? Capital A is a one-dimensional array. This is a one-dimensional array, which consists of n elements or n inputs. That is the indication. Capital A from 1 to n is a one-dimensional array which consists of n elements. That is, the inputs are, for example, written in this form: A1, A2, A3, etc., An. The greedy logic tries to find out a solution. So initially the solution is set to pi, that means null. Initialize a solution. Initialize the solution vector. Initially solution is set to null, right? There is no element in it, just an empty set. Since greedy works in terms of stages, one input is considered at a time. We have n inputs. That n inputs can be processed entirely. So writing for loop for I is equal to 1 to n do. So having n inputs, now we need to select one input at a time. So that input is, for example, stored in a variable x. X is equal to select of A. So when I is equal to 1, we are selecting the input. X is equal to select of A. That means AI, right? Actually, that can be taken any input, but only one input is taken. So select of A, this is the built-in function or a user-defined function that selects one input from the input list A1, A2, A3, etc., An, and it is assigned to the variable x. Then check if x is a feasible solution. If x is a feasible solution, for example, if SIBLE, if feasible x comma solution. That means here we are assuming that if x is a feasible solution, then this can be included into the solution vector. If x is a feasible solution, then solution is equal to union of x comma solution. If closes here, for closes here, n for. So after taking one input at a time, please check if it results in a feasible solution. So assume a feasible is a function, right, user defined function or a Boolean function that determines if x is a feasible solution. If x is a feasible solution, that means if x satisfies the given constraints of the problem, then x can be included into the solution vector. So assuming union, right, this is also a user defined function that combines the current solution with the input that we have considered x. So x and the solution are combined, and again the result is updated into the solution vector. Finally, we need to return the solution. Return solution. Opening curly brace here, closes here. This is the end of greedy method. End of a greedy method. So this is the general structure of a greedy method. Please think this can be compared with the general structure of divide and conquer algorithm, divide and conquer a comma n. There we are checked, right, if the problem p is small. If the problem p is small, we can find the solution directly. Else, applying the divide and conquer logic, the input size is divided into some k sub problems. We have obtained the solution of the k sub problems individually. Then the solutions of the sub problems are combined to form the solution of the original problem. In the same way here, we are considered the n inputs. One input is considered at a time. That's what we have introduced a for loop. For I is equal to 1 to n, only one input is considered at a time. Since x is equal to select of a, right, since we have the inputs a1, a2, a3, etc., an, based on the nature of the problem or based on the heuristics, one input, say a1 is first assigned to the variable x. Check if a1 results in a feasible solution. If it's so, that solution is included into the solution vector. In case if a1 is not feasible, right, then that input is rejected. Any input that does not result in a feasible solution is going to be rejected. That's what finally, right, we have a solution. This solution is clearly a subset of given inputs. Hope you understand. For I is equal to 1 to n works for n stages. When I is equal to 1, one input is taken. When I is equal to 2, another input is taken, say a2. When I is equal to 3, the third input is taken. When I is equal to n, say the nth input is taken. Here I have considered in an order. But when we solve the problem, optimization problem, we need not consider the inputs in an order, right? Same order, a1, a2, a3, etc., an. We can consider the random order, or we can consider some heuristic order, or we can make a specific order. Based on that, the inputs are considered to check for the feasibility. So any feasible solution that optimizes the given objective function, that is said to be the optimal solution. What is an optimal solution? any feasible solution that optimizes the objective function is said to be the optimal solution. So that stage we need to find out the optimization, either minimization or maximization. So the objective function is either minimize or maximize based on the constraints of the problem. This is the general form of a greedy method. So this greedy method works in stages considering one input at a time and check if it results in a feasible solution, then that is included into the solution vector. But when we solve the problem, we need to check if further the feasible solution that results in the satisfaction of our feasible solution is optimizing the objective function, so that we need to check if it's a part of the optimal solution. So this greedy strategy, this is applicable in solving wide variety of optimization problems. One of the optimization problem that we are going to consider here is with respect to a graph, that is a spanning tree problem. Spanning tree. So before going to see the term spanning tree, we have to look into the important term called weighted connected graph. Let it be indicated using the notation G. So a graph, right, G is assigned the corresponding edge weights, then it is said to be the weighted connected graph. For example, this is V1, this is vertex V2, this is vertex V3, this is vertex V4, this is vertex V5. Assuming that these are the edges, when these edges are assigned the positive real numbers, say 2, 5, 7.5, 8, 1, 3, 9, then the graph, right, G, this is said to be a weighted connected graph, because each edge is assigned the corresponding edge costs values, real numbers. In this we need to find out, right, what is called a minimum cost spanning tree. So before that, right, let's see, right, what is a spanning tree. Spanning tree is a tree that connects all vertices of the given graph. Spanning tree, suppose a T of a given graph G is clearly a tree with n vertices. A tree with n vertices. Assuming that G is a graph with n vertices, its spanning tree capital T is clearly a tree with n vertices. For example, V1, V2, V3, V4. This is the graph. Let it be G. For the given graph G, we can draw several spanning trees. For example, V1, V2, V3, V4. This is, say, T1. Since T1 is a tree with n vertices, since G is equal to V1, V2, V3, V4, right? G is having 4 vertices, n is equal to 4. In T1, right, we have n is equal to 4 vertices. All of these 4 vertices are connected, right, to form a tree. There is no circuit available in this T1. So T1 is one possible spanning tree. Likewise, we can draw V1, V3, V2, V4. We draw like this. This is, say, T2. T2 is also a spanning tree since all the 4 vertices are connected to form a tree. Then if we draw V1, V2, V3, V4, this is said to be T3. T3 is also a tree with n is equal to 4 vertices. Since T1, T2, T3, right, these are trees which are having exactly n vertices, same as that of the original graph G. So these are said to be spanning trees of the given graph G. Now just think of when G is assigned a cost, suppose 1, 2, 3, 4. Ultimately here this is 1, 4, 3, this is 2, 3, 4, this is 1, 2, 3. Now these are said to be cost spanning trees or spanning trees with edge costs are assigned. Now in this case we can find the total cost. For T1 the total cost is 1 plus 3 plus 4. For T2 total cost is 2 plus 3 plus 4. For T3 the total cost is 1 plus 2 plus 3. So we need to find out a spanning tree with minimum cost. So clearly here the spanning tree T1 takes a cost of say 7 plus 1 8, here 9, here 6. So we can find, right, some other spanning trees, right, if possible. So for the given graph we can find several spanning trees T1, T2, T3, etc. some at Tg. Out of all spanning trees we need to find the cost of the spanning tree, the total cost of the spanning tree that results in a minimum quantity. For example, in this case, given graph G, since we have 1 plus 2 plus 3, 3 plus 3 6, right, total cost is 6. This is a minimum quantity compared to, right, other spanning trees. So here T1, T2, T3, right, in that the minimum cost is 6. So this results in the minimum cost spanning tree, because minimum cost spanning tree is a spanning tree with a minimum cost. So we are going to define the term what is MCST, minimum cost spanning tree. Minimum cost spanning tree. Minimum cost spanning tree is a spanning tree with a minimum cost. So given the weighted, connected, undirected graph G like this, we can have several spanning trees. So each spanning tree can have its own total cost. Out of all spanning trees for the given weighted connected graph, we need to find out the spanning tree that results in a minimum cost, that is said to be the minimum cost spanning tree, say capital T, of the given graph G. The important fact is, since G is a graph with n vertices, clearly the minimum cost spanning tree T is also a tree with n vertices. A tree with n vertices has exactly n minus 1 edges. For example, this is a tree with 1 vertex. Number of edges E is 0. This is a tree with 2 vertices. Number of edges E is 1. This is a tree with 3 vertices, n is equal to 3, number of edges is equal to 2. So using induction, right, whenever we have a tree with n vertices, whenever a graph, right, G with n vertices, to construct a minimum cost spanning tree, you need to consider the same n vertices tree. So assuming for n vertices tree, we have exactly E is equal to n minus 1 edges. 1 vertex, 0 edges. 2 vertices, 1 edge, 2 minus 1. 3 vertices, 3 minus 1 edges. So clearly n vertices, n minus 1 edges. So given the weighted connected graph G, the problem is to find out the minimum cost spanning tree capital T of the given graph G. This is clearly the optimization problem. Optimization problem. The optimization problem minimizes the total cost of the spanning tree, minimizes the total cost of the spanning tree. Spanning trees are used in different applications. In electrical circuits, right, we can minimize the total cost. In different locations, right, if you want to connect all locations using cables, right, we can find out the minimum cost spanning tree so that the cost of the cables for the interconnection between the locations are going to be minimized. So clearly minimum cost spanning tree, right, for the given weighted connected graph G, determination, right, this is an optimization problem that minimizes the total cost of the spanning tree. In this case, this outcome, minimum cost spanning tree, for example, here, this is the list of edges included in the solution vector, say V1, V3, V1, V3, V3, V4, V2, V4, V1, V3, V3, V4, V2, V4. So these solution edges or solution vector is clearly the subset of the original problem, because the original problem edges are V1, V3, V3, V4, V4, V2 and V1, V2. Clearly the T3's edges are subset of the original edges. So whenever we have the optimization problem, that results in the subset of inputs as the solution vector, then that problem can be solved by applying the greedy design strategy. Greedy design strategy. So clearly minimum cost spanning tree for the given weighted connected graph can easily be applied using the greedy method, because the outcome of minimum cost spanning tree is the subset of the given inputs for the problem. So in this session, we have discussed the different algorithm design strategies, say divide and conquer, greedy method, backtracking, branch and bound, right? These are several algorithm design strategies: divide and conquer, greedy method, dynamic programming, backtracking, then branch and bound. We have focused on, right, what is a greedy method, the general form of the greedy method, how the inputs are taken and how the inputs are processed to form to the solution vector, and how the solution vector is clearly the subset of given inputs. And we have seen, right, what is a spanning tree and what is the cost associated for total cost associated for the spanning tree. Then how to find out the spanning tree with a minimum cost, right? There is a minimum cost spanning tree, and we have seen the greedy method is applicable in solving the optimization problem. For example, to find the minimum cost spanning tree of the given weighted connected graph. So in this session, right, we have seen these topics: algorithm design strategies, general form of the greedy method, and the fundamental in minimum cost spanning tree. In the next session, we focus on how to find the minimum cost spanning tree for the given weighted connected graph using Prim algorithm. Okay, thank you very much.